Okay, so today we're going to finish up chapter 8, and then I sent out a invite for tomorrow evening, and I think I put on we're going to do that at the tutorial center, but I think we're going to do that in here. I'll send out another reminder, and I'll probably order pizza or something. It'll be dinner time. So we'll all gather in here, and what I want you to do is I want you to bring your inverted lecture that you got back from me today. Okay, and we're going to go through those problems in groups on the board, and we're going to work through how to work those problems better. Okay, so today we're going to finish up by talking about oxidation of alkenes and addition to alkynes. Okay, so as you might imagine, an alkyne is very similar in chemistry to an alkene. It's got pi bonds, right? What's the difference between an alkene and an alkyne? That's right, we have 2 pi bonds. I mean, in terms of the bonding, that's what's different, right? Now, of course, the shape is different. An alkene has what kind of bond angles around the carbon? An alkene. 120, right? It's sp2 hybridized, right? So it's trigonal planar. What about an alkyne, Allison? 180, linear, that's right. So there are some shape differences, but in terms of the chemistry, pretty much so whatever you can do to an alkene, you can do to an alkyne. It just typically happens twice, okay? With the exception of adding water across the carbon-carbon triple bond. It doesn't give you an alcohol, and we'll talk about why that is the case, okay? It does give you an alcohol as an intermediate, but that then does what's known as a tautomerization, and we'll talk about why that's the case, okay? So, one of the things that we can do to alkenes is we can add H2O2 across the carbon-carbon double bond. Now that's essentially peroxide, right? And we get what are called vicinal diols, okay? These vicinal diols, you do not get them by just simply taking the alkene and mixing it with hydrogen peroxide. It doesn't work that way. You have to have another reagent to do this. And it turns out there are 2 reagents that are typical for doing this that I'm going to hold you responsible for. The first is potassium permanganate in basic solution. It will add 2 OHs in a vicinal fashion across a carbon-carbon double bond. Okay? Is that syn addition or anti-addition? It is syn addition. That's right. The other is to use osmium tetroxide in the first step, followed by a treatment with sodium bisulfite and water, and you can get syn addition of OH, or 2 OHs, excuse me, across the carbon-carbon double bond. Okay? Where are these diols useful? Where do you all know about these diols? They are useful in steroids, that's true. I'm thinking more practically, though, on a day-to-day basis that you might come into contact with. Your automobile probably cools itself with some of these things. Antifreeze, ethylene glycol, although ethylene glycol has largely been replaced by propylene glycol in automobiles. Nonetheless, ethylene glycol, 2 carbons, 2 OHs, has been a traditional use in automobiles. Does anybody know why we've gotten away from ethylene glycol and gone to propylene glycol?
It's sweet and it's very poisonous.
Well, which one? Ethylene glycol is very, very sweet and very, very poisonous. That's exactly right. Dogs do like to drink it. I mean, if you've ever tasted it, don't go and taste it, please. But if you ever have, and I had the misfortune of having a small taste at one time, it is extraordinarily sweet. Oh, yeah. Oh, you would want it.
Apparently, the only treatment for like dogs that have eaten the ethylene glycol is to get them drunk.
That's right. That's exactly right. Make the liver work on the ethanol as opposed to ethylene glycol, and so they can excrete. Huh? Medical vodka. That's right. That's right.
I remember my mom going there at one point. They had a problem with the medicinal vodka going missing from the pharmacy. Because they have to have so much of it on hand in case somebody comes in with this fake poisoning.
Yeah.
But it would keep going.
Yeah. No sense in letting it go bad on the shelf, right? Anyway, these are the 2 ways in which we can make these so-called diols, vicinal diols. also known as glycols. Obviously, that's where we get the name ethylene glycol. So there's a lot of names that they can go by. The reason we get syn addition is because of the shape of the what the metal species looks like. So this is a Lewis structure for the permanganate ion, the anion. And as you can see, you've got 3 atoms that are involved, the oxygen, the manganese, and the other oxygen. And those 3 atoms can only approach from one face of the alkene, either the top or the bottom, it doesn't matter. Okay, they're equivalent approaches. But you can't have one oxygen on one face and the other oxygen on the other face. There just isn't enough distance there to do that. Okay, and so you can't get anti-addition of the 2 OHs. And so what happens is, does anybody know what the color of potassium permanganate in solution is? Purple, extremely deep purple. Okay, and you know that these reactions go very, very easily because when you take this purple solution and you add the alkene, what do you think happens to the color? It goes colorless. That's exactly right. If you don't have an excess of the permanganate. If you have a slight excess of the permanganate, it becomes a much lighter purple. But nonetheless, excuse me, you get the syn addition. We've just now made the 2 important carbon-oxygen bonds that we need. You can see why they have to be in a syn addition. And then water simply comes in and hydrolyzes the metal off, and you end up with the cis diol. The same sort of mechanism is true for the osmium chemistry, except osmium tetroxide is neutral. It's not an anion like we have for potassium permanganate. The mechanism at the first step is essentially the same. You end up with this osmate. You can see why the oxygens are now syn to one another. However, this metallic intermediate is actually fairly stable to water, and so you have to reduce it off with sodium bisulfite. That's why you have to have a second step. And that then removes the osmium, and you end up with the 2 H's. What do you all know about osmium? Where's it at on the periodic table? Yeah, it's in the iron family, right? So it's right down here. What else do you know about it? It is? What else? Can, that's true. Anybody know anything about how expensive it might be? Or how toxic it is? Osmium is extremely toxic. Okay? We have a small amount of osmium tetroxide in my laboratory, and we keep it locked up because of its toxicity. It can absorb through the skin, and it can kill you pretty easily. Okay? But it is a useful material because you can do this type of chemistry fairly easily. And now you might be thinking, well, if I can use potassium permanganate, by the way, they do use potassium permanganate to actually treat your drinking water to kill bacteria. So it's obviously not as toxic as osmium. We would never use osmium tetroxide to do that. And this is pretty cheap. Why do we need the chemistry for osmium? Well, we'll talk about that a little bit as well. Okay. Now, it turns out that as of the writing of this slide, which has been several years ago now, so these prices are surely much more expensive. Potassium permanganate costs from Sigma Aldrich, which is already an inflated price, $20.63 per mole. So if Nathan comes in and he wants to do this chemistry and he wants to take a mole of alkene and make a mole of glycol, he would need a mole of potassium permanganate, and he'd have to spend $20.63 to do that. If Terry, however, came in and said, you know, I want to do that same chemistry, but I want to use osmium, she's going to find that a mole of osmium tetroxide is going to cost her 40 grand. Who's going to get to keep their job and who's going to get fired? Right? 40 grand, that's a lot of money. Osmium's expensive, okay? So she would take something that costs 40 grand and make a product that costs a few bucks. That would get you fired, right? So it turns out you don't need to use the osmium in stoichiometric amounts. What do I mean by that? All right, that means I can use it in a catalytic amount. I can use just a small amount. In the process, if we count up the oxidation state, what happens, osmium tetroxide starts off in the +8 oxidation state for osmium. And when it delivers its 2 oxygens, the byproduct that you get for osmium is an osmium in the +6 oxidation state, which is inactive. So all we really need to do is take osmium 6 and oxidize it back to the osmium 8 oxidation state. and it can be reused again. The way that we do that is using a molecule known as NMO. That's this molecule right here. It stands for N-methyl morpholine N oxide. Okay? Now, N-methyl morpholine N oxide can oxidize osmium-6 back to osmium-8. And why is that important? Because NMO only cost me $190 per mole. That's a lot less than 40 grand, right? I think you all will agree with that. Okay? And so even though we can get away with using potassium permanganate, which only costs $20.63 a mole, right? That's still a lot cheaper than NMO. So why is it that we need this osmium chemistry? Can anybody tell me from your reading? Why is it that I need this expensive hammer when it seems like I've got a cheaper one that'll do the same job? I can reuse the osmium over and over. That's right, so it's catalytic. That's one good thing about it. What else? Are there any problems with the potassium permanganate chemistry? It turns out that the potassium permanganate chemistry is not as well behaved as it's written on paper. It will make the syn-diol, but if you let it warm up too warm or you let it run too long, that syn-diol will further oxidize into carboxylic acids and not give you the diol. The osmium chemistry does not do that. And so that's the reason we need that other tool in the toolbox, because the potassium permanganate on paper seems ideal, but in reality it actually can over-oxidize your products and give you products that you don't want. So that's the reason why we need additional tools in our toolbox. And so chemists have had to come up with a way to avoid this 40 grand per mole problem. And truth be told, I inherited this osmium tetroxide in my laboratory, and the reason I didn't get rid of it is because if I ever need a stash of cash, I'm going to go sell some of it, okay? I've probably got 4 millimoles, so that's a few grand, right? So if there's ever a black market around here for osmium tetroxide, you might see me on the street corner. That little bit? Well, it would be a few $1,000s.
So, I mean, like, if you're like looking at it like in the bottle.
Oh, the bottle's about that big, and it's got about that much in it, something like that. Yeah, it's more expensive than gold. Everybody thinks that gold is the thing that everybody really wants. Gold, I mean, you can go to Alaska and dig it up out of the dirt, right? Go dig up some osmium tetroxide up out of the dirt. You know, you really can't do that, okay? So, the take-home message, we can make cis-diols or syn-diols. They're also vicinal diols, and they're also known as glycols, right? Very good. And we can make them through two routes. Potassium permanganate under basic conditions, it must be kept cold, or osmium tetroxide followed by treatment with sodium bisulfite and water. Two-step process. Now, another thing that we can do to alkenes is we can actually oxidatively cleave them. Thank you. We can oxidatively cleave them through a process known as ozonolysis, but we'll get to those details in just a moment. What's kind of unique about this reaction and kind of sets it apart from the other reactions we've been talking about in this chapter? Yeah, that's right. And every other reaction we've been talking about, right? We've been talking about adding things across the carbon-carbon double bond. What are we doing here? We're taking an axe and chopping right through that carbon-carbon double bond, both the sigma bond and the pi bond. We're breaking both a weak bond and a strong bond in one fell swoop. But what are our products in that example reaction up there? A ketone and a aldehyde. That's exactly right. So which carbon of the alkene did the ketone come from? Carbon 1 or carbon 2 is reading from left to right. Carbon 1, and how do you know that? It's got the two R groups attached to it, right? This carbon has the two R groups attached to it, so it's going to become the ketone. And the aldehyde must be this carbon, right? And it's an aldehyde because it has both an R group and a hydrogen, right? This is the easiest reaction for you all to remember because there's no rearrangements. You simply just cut the carbon-carbon double bond in half and replace with a carbon-oxygen double bond. It's just that easy, okay? Now, the way that we do it is not quite so easy. We have to use ozone to do these reactions, okay? So, what do you all know about ozone? We need it in the ozone layer. Protects us from sun's radiation, UV light. What else do you know about ozone? Okay, what else do we know about it?
Generally gas.
Pardon? It is a gas, that's right. Makes it very inconvenient. What about ozone down here? Up in the ozone layer, it's really healthy for us. What about down here?
Bad.
It's bad, okay? And it's actually part of what happens in automobile pollution, right? This is one of the reasons to go to electric, because automobile pollution actually produces ozone. And ozone lower down in the atmosphere actually is not healthy for us. Ozone is a very reactive, very toxic gas. Do you think I can go down to the gas supply shop and just buy a bottle of ozone? Not at all. You have to generate it on demand. How do we generate ozone? How's ozone made in the ozone layer? Give me a good answer. That's true. Absolutely right. And how does that happen? So the atmosphere has O2 in it, right? Why is the ozone layer so high up? That's where all the sun's rays are, right? Or most of them, right?
Radiation energy.
That's right. We need radiation energy in the form of UV light to make ozone. And so you have to do the same thing in the laboratory. And you can buy these instruments called ozonators, which are these boxes, and people just treat them like a box. You hook in an oxygen source and you have an outlet. But in between in the box is a bright UV light, usually is the way that they do this. There's a couple of other ways they can do it, like arc, but the UV light is the most common. And as the oxygen passes through this, that intense UV light, you generate small quantities of ozone, which then you bubble through the reaction that you want to do. They're a big pain in the rear to use. I've used them one time in my entire career, and I swore I would find other ways to do the chemistry that I wanted to do. Because you're just never sure how much ozone you're generating. It's not like you have an ozone meter there that goes, hey, this is going well, it's not going so well. You know, you've got this bright light that you have to protect yourself from, and you've got this reactive gas coming out the end that can catch on fire and all this kind of stuff. So while it sounds cool, it's really a big pain. So what you do is you bubble through ozone for a while through your solution of alkene. Typically you take your alkene and you dissolve it up in something like methylene chloride. And these reactions are typically done at fairly low temperature. And then after you're confident that you've added enough ozone, you then treat it with zinc and water, and you get your products. In this case, we get a ketone and an aldehyde. So we would end up with our good friend acetone and acetaldehyde, and the reaction would go to completion. And over this two-step procedure, basically what we've done is just chopped the alkene in half and replaced on each one of these carbons an oxygen. Okay? So, pretty simple process overall on paper anyway. You can also use another molecule called dimethyl sulfide if you don't want to use zinc and water and do exactly the same thing. What do you know about zinc? Is it a reducing agent or an oxidizing agent? What do you remember from Gen Chem? Zincs have a lot of metal. Is it? Why is it a reducing agent?
Because I remember seeing it in combination with O and O. Oxygen is obviously an oxidizing agent, so therefore it must be reducing.
Okay, good enough rationale. Zinc by itself in the metallic state has a lot of electrons and it likes to give them up, right? And so it's a reducing agent. So if I need to do the oxidation followed by a reduction to get my products, what do you think the purpose of the dimethyl sulfide is? It's a reducing agent. Sulfur has lone pairs of electrons. It can function as a reducing agent. Zinc and water, do you think this is going to be homogeneous or heterogeneous? If I take my solution and then add zinc and water, is it going to be a homogeneous solution or a heterogeneous solution? It would exactly be heterogeneous. And what do you know about heterogeneous reactions compared to homogeneous reactions? Not as fast. That's right. So this step works a little slower. Now, what do you think about the solubility of dimethyl sulfide in an organic solution? Very high, right? So we can add this and quickly reduce the intermediate that we're going to talk about in just a moment to the products. The problem is, if you came to my lab, we're going to use zinc and water. We're not going to use dimethyl sulfide. Anybody know why? It can catch on fire very, very easily, but more importantly, zinc is cheaper. Yeah, that's not too bad. Anybody ever smell a skunk? Take like 1,000 skunks and compress them into a room, and that's kind of what dimethyl sulfide smells like. It's bad. Bad, 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 bad. Bad stench. Okay, and so we try to avoid that at all costs. So I'll take the fact that it's going to take an hour or so to do this top one, where this is over in a few minutes. That's okay. Zinc doesn't stink. And so I don't have to worry about your handling of the material skills. Okay? But nonetheless, either one of these will work just fine on paper, and you can end up with your products. Okay? Now, the mechanism, I want you to know, is fairly complicated. I do not expect you to be able to push arrows for this mechanism at this level. But what I want you to understand is that there's a couple of intermediates along the way. And the reason that this is thrown into this chapter is which step? Which step of this mechanism is the reason why this reaction, which seems out of place, is actually put in the addition chemistry of alkenes chapter? The first step. Yeah, it's the addition, right? You're adding 2 oxygens across the carbon-carbon double bond, right? Here's what ozone looks like. It's an addition, and you end up with what's known as a malozonide, which then rearranges to an ozonide. And during that rearrangement, we've officially broken what? Which bond? Well, we broke the double bond or the pi bond in the first step, right? That's right. The second step is breaking the sigma bond. So by treating a carbon-carbon double bond, right, which has a pi bond and a sigma bond, when we add ozone, we're breaking the pi bond in the first step. And that makes sense because the pi bond's the weaker, right? You end up with this malozonide, which is actually detectable, and then you give it some time and it rearranges to this ozonide. And then if we use zinc and water, what's it essentially doing? Okay, but it is reducing, that's true, right? But what is it essentially doing to my molecule, to my ozonide? What is it removing? It's removing an oxygen atom. That's right. So in the process, we're removing one of these oxygen atoms by the reducing agent. So this is being reduced to, in this case, 2 ketones. And if we use zinc, we get zinc hydroxide as the byproduct. If we use dimethyl sulfide, we end up with, what's this one? It's one of those polar aprotic solvents we talked about. DMSO, that's right. So we get DMSO as a byproduct in this particular reduction. So it turns out dimethyl sulfide stings like no tomorrow. DMSO has essentially no odor. And so that's one way you could test it. You could just put your nose in there and then, oh, it doesn't stink anymore. Waft it. You get a waft of that, it's gonna knock you out. It's pretty bad stuff. So here's a couple of examples of where we can do this type of chemistry. This is limonene. Where does limonene come from? Not limestone. Actually, it comes from citrus fruit. So it does exist in the peel of limes, lemons, and oranges. Okay? You all next semester in one of your first labs in 256, you're actually going to isolate limonene from oranges. Okay? Is this molecule chiral or achiral? You got a 50-50 shot, and you just saw my face with the achiral. So Matthew's our hero. It is a chiral molecule. Where is the chiral center? There? Yeah, there you go. Good. That's exactly right. So we can have R-limonene and we can have S-limonene, right? And it turns out that you'll get one in one type of citrus fruit, the other in another. Does anybody know why the citrus fruit produces limonene? What are citrus fruits always trying to avoid? Infestations by what? What insects? Fruit flies, right? And it turns out that limonene is a very, very effective insecticide, okay? So if you ever take a piece, if you go to lunch today and you get an orange, take a piece of the peel and kind of hold it away from you a little bit, but kind of get it kind of close and push on it. And the stuff that comes out that has the citrusy odor, it's limonene. I mean, it produces that much limonene.
So if you're having a truck and double one fruit flies, you get a bunch of orange peels?
Yep, you can, actually. Yeah, that's exactly right. So orange peels contain a natural insecticide. It turns out, because for those of you who cook, you probably have used orange peel in things like cakes, right? Zest. So is it toxic to humans? No. So this is actually a very environmentally friendly insecticide. And some of your fire ant killers that you go and buy, if you buy the green ones, they are usually just a solid support that contains limonene coated on it. And they will smell kind of citrusy. And you go out and you put those on your fire ant beds, and it'll kill the fire ants. Okay? That's a good question. I don't know the answer to that one. I just know it is very effective. I was a teaching assistant at the University of Oklahoma one summer for the National Science Foundation Teacher Institute. And one of the things that we had them do was actually isolate limonene, and then we had these tubes full of so many fruit flies, and they would put a drop of the limonene on top of the cotton plug, and then they'd count how many fruit flies died. All of them died. So it's a very, very effective insecticide, actually. It's also used these days as an industrial solvent. You can go to the auto shop these days and buy engine cleaners that contain limonene. And the reason that we do that is because it's a hydrocarbon, right? So it'll dissolve things like grease and motor oil and that kind of stuff, but it's not toxic to humans. It's relatively environmentally benign. So if you're out working underneath the shade tree on your pickup truck and you go to spraying this on an engine and it drips down on the ground, no ants are going to be there, but who cares, right? No fire ants anyway, okay? So it's a very useful industrial solvent because it's relatively environmentally benign and it can still dissolve grease and grime and all that kind of stuff. But notice it contains two alkenes within this molecule, right? And so if we were to take this and treat it with ozone followed by dimethyl sulfide, we're going to break those carbon-carbon double bonds and replace them with carbonyls, right? So we're going to take the alkenes and get carbonyls. So if we break this carbon-carbon double bond, right, we're going to end up with what here? What's that functional group? Carbonyl. Yeah, what's a carbonyl? But it's which one? It's a ketone, right? Because there's an R and there's an R. So we've got a ketone. This carbon becomes an aldehyde. Okay, now all this is connected together, so this all stays together, right? And so this carbon now becomes a what? A ketone, and this one gets chopped off completely and becomes, okay, this is a special aldehyde. Which aldehyde is this one? This is formaldehyde, because one of the R groups, right? Both R groups here are both hydrogens here. One is the hydrogen, one's the R group. I'll get it out straight here in just a second. All right, what do you know about formaldehyde? It is. It's embalming fluid, that's right. It's what you preserve your frogs over in the biology department with, right? Formaldehyde solutions. Huh? It still smells like formaldehyde over there. Maybe. But yeah, this is used in embalming fluid. So you can chop these things up and make new functional groups. Okay. We can do the same thing to carbon-carbon triple bonds. We can actually cleave the carbon-carbon triple bond. But in doing so, we are not going to end up with aldehydes and ketones. What's the overall functional group transformation here From an alkyne to a carboxylic acid. That's exactly right. So if I take an internal alkyne and I treat it with ozone, notice I don't need to use zinc here. It's just water treatment in the end. You're going to clip that carbon-carbon triple bond completely in two, and you're going to replace it with a carbonyl and an OH. And of course the OH comes from the water, and so you end up with carboxylic acids. So you're learning now how to make carboxylic acids, you've learned how to make ketones, you've learned how to make aldehydes by this oxidative cleavage of pi bonds and sigma bonds, right? So here, since this is an internal alkyne, we end up with two different carboxylic acids, right? This carbon is this carbon, and I know that because it has the ethyl group attached to it. So I've got ethyl and then the carboxylic acid, so that has to come from this part. And here I've got a methyl and then the carboxylic acid, and so that has to be this part right here. So carbon-carbon triple bond, we get carboxylic acids. However, if I start off with a terminal alkyne, the products are a little bit different. What do I end up with here? And carbon dioxide, that's exactly right. So this obviously is this carbon, and this carbon becomes the carbon dioxide. So terminal alkynes, you can chop off that end carbon as carbon dioxide through this ozonolysis procedure, okay? Now, like I mentioned, we can take carbon-carbon triple bonds, and we can do a lot of the same chemistry that we learned about in the alkene addition. We're just going to do it twice. So remember, we had that original reaction where we were just adding a theoretical reagent XY across a carbon-carbon double bond. Well, that'll happen here, and you end up with a remaining weak pi bond that can undergo a second addition, okay? And so we're replacing two weak pi bonds with how many strong sigma bonds? 4. So should this reaction lie to the right or to the left? To the right. That's right. These reactions occur pretty well, actually. I mean, they essentially go to completion for the most part, okay? And so as you can imagine, we can add almost all the same things that we added before. If we take an alkyne and we react it with 2 moles of HX, where X is Cl, Br, or I, we can end up with hydrohalogenation. It just happens twice. What's kind of strange about this, however? Where is the halogen always ending up? On the same carbon. Is this Markovnikov addition or anti-Markovnikov addition? It is Markovnikov addition because the hydrogen went to the carbon with the most hydrogens, right? And the halogen goes to the carbon with the least number of hydrogens. It just happens twice. So it's a double Markovnikov addition of HX across a carbon-carbon triple bond, okay? Now you might be asking, why does the X go to the same carbon both times? We'll talk about that in a minute, okay? We can add halogens across the carbon-carbon triple bond, just like we did a carbon-carbon double bond. We're just going to do it twice, okay? What's different is when I add water across a carbon-carbon triple bond. What do I get here? I don't get an alcohol. What did I get? I got a ketone. Let's see why that has to be the case. So, mercury is sometimes used in these reactions as a Lewis acid. I'm just going to use this. What's the first step of the mechanism? Think about the alkene addition, or alkenes in addition of water. What's going to happen here? What's the first step? What do you think, Gabby? What do you think the first step is?
The hydrogen's going to be attracted to the triple bond because it's acidic.
All right, so we're going to have an arrow like that, right? And let me draw this a little more accurately. Does that look like a stable carbocation or a pretty reactive one? And why?
Because it's already bonded to two other carbons.
All right. This is what's called as a vinyl carbocation. They can be generated, but they're very high in energy. Okay? They're very unreactive because it can't planarize like a carbocation wants to. It becomes a problem, right? So it's very, very reactive. Now what happens? Got a lot of water around. That's right. And so we end up with which looks like an alcohol, right? That is not an alcohol. What is the name of that functional group? When an OH is connected to a vinyl carbon, it has a special name, and it's called an enol. Where do we get that name, enol? An alcohol and an alkene. That's right, enol, right? Enols are not stable. Okay? They tautomerize. What does that mean? They do. What's actually happening going from here to here? Okay? How? All right, so the double bond is going over to the oxygen. If I do that, I'm going to exceed the octet for oxygen. But it seems that that's what's happening, right? So what else can I move? All right, I could move that bond, yeah. So let me draw it like this for clarity. Right? So what's going to happen? Here, right? And what's going to happen to this bond? It's going to pick up the hydrogen. So that hydrogen that's on the alcohol is actually one of these hydrogens, and we end up with the carbon-oxygen double bond. And it turns out that the ketones are more stable thermodynamically than the enols. And so the equilibrium lies to the left as I have it here, or to the right? To the left. That's exactly right. This is called a tautomerization. So I draw it kind of like an equilibrium, because you will have some of the enol present, but it'll be a very small amount, very hard to detect actually. The enol gets formed as an intermediate, which rapidly tautomerizes to the ketone. This is why you don't add OH or H2O across the carbon-carbon triple bond twice. Because once it adds the first time, you end up with an enol, which rapidly tautomerizes, and you end up with ketones in this case. Okay? So you end up with a ketone when you do a Markovnikov addition of H2O across a carbon-carbon triple bond. Okay? So yeah.
Can you explain again why it's called an enol?
Sure. So ene for the alkene, all for alcohol. So it's taking both of those functional groups together and making one name. Okay? This is what happens when we hydrate an alkyne. So you have just learned today 2 ways to make ketones. Right? What was the first way? Okay, so ozonolysis of an alkene can make ketones, and hydration of an alkyne, we can make ketones. Okay, so we can make ketones now pretty quickly. The number of tools that you all are going to have in your toolbox is going to start getting pretty heavy. Okay? The mechanisms that we need for the rest of the 2 semesters, you pretty much so have in hand now. Now it's just putting the different tools that we need in our toolbox so that we can do a bunch of different chemistry. Okay? So, why is the second one different? Why do I end up with an aldehyde and not a ketone here? What is BH3 followed by H2O2 in base? It's an anti-Markovnikov addition of water across the carbon-carbon pi bond, in this case, right? So what would, if we did that here, what would the enol be? It would be that, right? Because we do the hydroboration first, and that puts the boron here and the hydrogen there. And then we, in the second step with the peroxide and base, right, we remove that boron and put the alcohol on. And so we end up with an enol, but when this one tautomerizes, it tautomerizes to a aldehyde. Okay. So if Paige wants to make aldehydes from alkynes, you need to use the hydroboration oxidation sequence. If you want to make ketones from alkynes, we use the hydration using water, sulfuric acid, and a little mercury sulfate. The mercury's there as a catalyst. Okay, you can really think of this reaction just with sulfuric acid and water, and in fact, it will work just fine. The mercury sulfate just speeds the reaction up considerably. Okay, so essentially, we're doing the exact same thing to alkenes, or to alkynes that we did to alkenes, with the exception of water, right? Water gives us ketones and aldehydes. What else can we add across that carbon-carbon triple bond? That I don't have listed. I can add 2 hydrogens. So let's say we start off with this alkyne. And let's say Matt takes hydrogen gas and palladium. What does he get? What's the product? An alkane. That's exactly right. Why not an alkene? It will react as well. You can't really control the amount of hydrogen you have. It's a gas. It's hard to do. Once you form the alkene, it's as reactive as the alkyne, and it continues to react. However, we can reduce an alkyne to a cis-alkene by adding a single equivalent of hydrogen using what catalyst? Lindlar's catalyst. Which is palladium on barium sulfate and lead and poisoned with quinoline. It's a mixture of stuff, okay? There's another catalyst that your book talks about. Does anybody know what it is? It's called nickel P2 catalyst. It'll do the same thing, okay? It's a nickel boride species, okay? And it'll do essentially the same thing. So if Paige comes into the lab and she has an alkyne, she wants to make a cis-alkene, she's going to use Lindlar's catalyst or nickel P2, okay? But maybe Jamie comes in and she wants to make a trans-alkene. What do we use there? And we've talked about this one. We're not going to use Lindlar, right, because that'll give us the cis. We're not going to just use palladium. That'll give us the alkane. So what reaction conditions will we use to add a single equivalent of hydrogen across a carbon-carbon triple bond in a trans fashion? Hydroboration won't do that. All right. Lithium metal, that's a good start. What else do I need? What was the solvent? Liquid ammonia. Lithium and liquid ammonia. And we called this what kind of a reduction? Don't all speak up at once. That's the result, but that's not what we call it. It is a trans reduction of an alkyne to an alkene. Dissolving metal reduction, DMR. It's the dissolving metal reduction. That's exactly right. Just for your information, lithium in liquid ammonia is the prettiest blue color you'll ever see in your life. Better than any ocean blue, better than any sky blue. I mean, it is just phenomenal to look at. It's mesmerizing, actually. Blue's one of my favorite colors. So, okay? It actually is thought to be, when you take lithium and put it in liquid ammonia at minus 38 degrees, that blue solution is because there are free electrons in solution. Who knew it, that free electrons were actually blue in color? But they are. So you have this solution of electrons that you are adding to this alkyne. We're not going to go through the mechanism yet because it's a free radical mechanism. It's a single electron addition at a time, okay? And it uses that single barb hook arrow. We're going to talk about that in chapter 10, okay? We'll talk about it. But we can actually get transalkenes by the dissolving metal reduction. We can get cisalkenes by the Lindlar or nickel P2 reduction. And we can get alkanes by simple reduction using palladium. What other metals would work here for this? Nickel or platinum. Are there others? Yes. It actually turns out pretty much so. Most of the stuff in this region right here will work. Ruthenium, rhodium, palladium, platinum, nickel, iridium. There are hydrogenation catalysts for all of those. And it turns out that palladium is one of the least expensive, although palladium is still a lot more expensive than gold. Okay? So is it catalytic or stoichiometric in platinum or palladium? It is catalytic, so this is catalytic hydrogenation. Okay? You all have probably eaten solidified vegetable oil, which is partially hydrogenated, and they partially hydrogenate it with these catalysts. All right, so that finishes us up for today. We will finish this up on Friday, okay?